We've been told for years that putting computers behind the wheel will cure traffic congestion. The logic is straightforward. Remove slow human reaction times, and vehicles will flow together in perfect, uninterrupted harmony. Today, that responsibility falls primarily on one technology already deployed on public roads, adaptive cruise control, or ACC. But macroscopic traffic simulations reveal a serious problem. Instead of smoothing the flow, commercial ACC systems are actually generating phantom traffic jams. To maximize road capacity, engineers program these systems to maintain short time headways, packing cars tightly together to increase throughput. Operating at these tight tolerances leaves the system highly vulnerable. Even a fraction of a second of radar estimation delay creates a lag in the control loop. Traffic engineers refer to this specific vulnerability as string instability. Applying local automation without broader systemic awareness does not eliminate human error. It simply automates the creation of traffic shockwaves. Consider a row of highway traffic. A single lead vehicle taps its brakes, creating a microscopic drop in velocity. The first following vehicle registers this change, but the processing delay forces its controller to brake slightly harder to maintain the programmed safety gap. That harder deceleration forces the vehicle behind it to brake even more sharply. The initial minor speed drop is amplified as it travels upstream through the platoon. This happens because of a strict hardware limitation. Standard ACC sensors only evaluate the distance and speed of the vehicle immediately in their direct line of sight. The traditional engineering fix for this is cooperative adaptive cruise control, a system that requires vehicle-to-vehicle or V2V communication networks to share braking data instantly. However, V2V networks require near-universal market penetration and standardized infrastructure, meaning they cannot solve the congestion problem on today's roads. Optimizing the behavior of a single car based solely on its immediate predecessor results in the failure of the larger platoon. To understand why this fails, we look at the standard ACC third-order kinematic model. The controller calculates output based on three inputs: the distance to the leader, the lead vehicle's velocity, and the ego vehicle's speed. The system processes these inputs to command acceleration, but the driveline requires time to respond. Add the radar's processing time, and you introduce an unavoidable estimation delay. We can evaluate the stability of this specific closed-loop model using the complementary sensitivity criterion. This chart shows the transfer function for the standard ACC controller. The blue line represents response magnitude across frequencies. Where it passes the 1.0 threshold, the resonance peak indicates the system amplifies input signals rather than dampening them. This translates into a step response chart, showing what happens when a leader suddenly changes speed. The blue line significantly overshoots the target velocity. In the physical world, that mathematical overshoot manifests as the vehicle braking much harder than necessary. The mathematics prove standard ACC control equations actively destabilize traffic flow. There is a hardware-level alternative that does not rely on external V2V networks: radar-based multi-anticipation, or MACC. Modern radar exploits multipath propagation, bouncing waves beneath the vehicle in front to detect a second car further ahead, entirely outside the direct line of sight. This adds a new layer to the state space formulation. The control law now incorporates the physical distance to the second leader and factors in that second leader's relative velocity. A design parameter called omega is introduced as a trust coefficient, weighting the influence of the second leader against the first. This chart shows the original transfer function, now updated with a violet line representing the new MACC logic. The resonance peak is entirely crushed. The system's response stays firmly below the instability threshold. This dampening isn't achieved by simply scaling up the original control gains. It works because the new inputs change the dynamical matrix of the system itself. MACC resolves string instability using strictly local, onboard physics, decoupling highway stability from the limits of external infrastructure. Traffic engineering has long been constrained by a zero-sum trade-off. High flow requires short headways between vehicles, but short headways historically destroy stability. This chart maps flow against stability, defining a strict Pareto optimality set for standard ACC capabilities. The red area illustrates the absolute limits of the traditional system. By introducing the MAAC control law, the blue MAAC region is added, shifting the optimization curve outward. With this expanded stability region, engineers can safely iterate the target time gap downward without triggering shockwaves. The system achieves higher theoretical road capacity while maintaining the exact same stability metrics as slower, widely spaced traffic. MAAC breaks the zero-sum constraints of highway design. High density and smooth flow are no longer mutually exclusive. Theoretical closed-loop dynamics prove the concept, but real-world microscopic traffic simulations tested against chaotic environments. In real-world mixed traffic, unpredictable human drivers actively exploit the precise wave-dissipating gaps maintained by automated vehicles. A sudden lane intrusion forces the MAAC vehicle out of its optimal state and into a severe reactionary braking fallback to restore safety margins. That severe fallback triggers the exact upstream shockwave cascade the algorithm was engineered to prevent. To absorb and dampen these human-induced disruptions, a critical threshold of vehicles on the road must be equipped with MACC to establish collective network resilience. Meaningful congestion reduction requires control laws capable of anticipating the broader system state. Isolated optimization fails when introduced to a globally connected physical environment.